So in the last video, we continued to take a look at simple harmonic motion to develop a better understanding of the pendulum. Now here we're going to go into waves. And I will point out that from a physicist's perspective, a wave is a wave is a wave. And much like we saw with simple harmonic motion, any system that you can massage into looking like a certain key relationship is a simple harmonic oscillator. Same kind of deal with waves. In fact, it'll turn up that waves will show up in a major way 3 times in a introductory treatment on physics. The first, and the kind that we will be concerning ourselves with here, is our mechanical waves. These are waves that are based on the displacement and restoration of material, and that's going to be the focus of what we're going to do for the rest of these videos. However, it's well worth studying because when you go on to look at electricity and magnetism, you'll discover that light is an electromagnetic wave. C-T-R-O, magnetic. It's an electromagnetic wave. And here, there's no material being displaced, but it turns out that things called electric and magnetic fields, which you'll learn about later, will mutually oscillate in a way that winds up looking mathematically identical to a mechanical wave, mathematically, not actually physically. These waves will always propagate at the speed of light, and in fact are what light is. And then usually right at the very end of a introductory survey sequence, you'll go and take a look at matter waves. At the end of the 19th century in physics, there was a bit of a crisis that had started to develop. And it was looking like for all practical purposes, we were done with physics. We had a good theory of electricity and magnetism, and we had Newton's laws of motion to describe everything. And there were just a couple of small little issues remaining. One was that black body radiation didn't work the way you would expect, and another was that the photoelectric effect, which is the basis of how solar cells work, didn't work the way you would expect in that framework. It turned out that it was impossible for the classical framework of physics to answer those, and so in the late 19th and early 20th century, the physics community pretty much had to jack the entire house of physics off its foundations, tear out the foundation, pour a whole new basement, and then carefully set the house of physics onto a better, more solid foundation. One of the key bits in that new foundation is it turns out that absolutely everything has both a dual wave and particle nature. So for instance, light can not only be described as a wave, it can also be described as a particle, which we can call a photon. And ordinary matter, which we normally think of as particles, can also be described as waves, which becomes the foundation of quantum mechanics. Here, what the wave-like property is doing is it's dictating the probability that we would detect a particle in a certain location should we go choose to look for it at that location. So these seem like wildly different things, but mathematically the underpinnings are the same. And so when you get to electromagnetic waves, you'll say, oh, these are like magnetic waves except for da 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 da. When you get to matter waves, you'll say, oh, these are like mechanical waves except for da 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 da. So it's well worth studying mechanical waves. So we'll focus on mechanical waves. And so an example that I can think of is, let's say you're standing here at the banks of a pond. All right. And you then go ahead and decide to throw a rock into the pond. Well, what will happen when the rock lands there? Well, you know that you see ripples of water propagate out circularly in all directions around it. Now, so what we have is a propagating disturbance in some medium, and we'll use that as our definition of a mechanical wave. There we go. Now, importantly, the medium doesn't move with the wave. Let's say there was a little plastic toy boat sitting right here. What will happen is that boat will just bob up and down, but it won't move side to side. So another key result here is that the medium does not move with the wave. But we do know that waves can carry energy and momentum. You can verify this by, after putting on suitable hearing protection, cranking your stereo way up on something with a good bass line, putting your hand in front of the subwoofer, and you'll feel the gusts of air striking your hand. The fact that you can feel that means that your hand is feeling an impulse, and that can only happen if we are transmitting, if we're carrying momentum. And since it's doing work on your hand, there must also be a transmission of energy happening. All right, so with that, these mechanical waves can be divided into two subcategories. The first of these are called transverse waves. So in a transverse wave, if we break the Greek roots apart, trans means across, verse the direction, so perpendicular to the direction. That's how you should read that. So this means that the waving happens perpendicular to the direction that the wave is actually moving. So for instance, if you have a rope or a string that you've fixed down at both ends, the wave would move this way, but if I focus on any individual piece of matter on the string, the displacement will happen that way. So that is a transverse wave. There are also what are called longitudinal waves. The classic example of these are sound waves. So as you're literally as you're listening to me right now, what is happening is your audio equipment is taking the electrical impulses that are that were generated when the computer file that represents my voice was decoded. Those electrical impulses get translated into mechanical motion, and there are different ways it can be done, but a typical way with a speaker is you have a magnet right here at the base of the speaker. And then there will be a coil of wire around the magnet that acts as an electromagnet. The magnetic field that that coil of wire generates will be moving in proportion to the waveform of my sound, and sound of this. And what will happen is that the magnet will oscillate back and forth like this. Now what that will do is that will cause alternately the speaker cone itself to flex, so it'll either compress air or it will leave a little bit of a vacuum behind. So and what I'm trying to represent here is these are compressions here, and then this region here would be a rarefaction. So a higher density of air, lower density of air. Now, if I look at a slab of air, it's just sitting here. So I'm just marking out a slab of air. What will happen is air molecules will come up from behind, give it a kick forward, it'll collide with the air in front, they'll give it a kick back, and so the slab of air will oscillate back and forth, parallel and anti-parallel to the axis, to the direction of propagation of the wave itself. So if the waving is happening perpendicular to the motion of the wave, that's a transverse wave. If it's happening parallel / anti-parallel, that is a longitudinal wave. Now, it's beyond the scope of this presentation to derive the mathematical form of a wave, but we can write it down and then we can see that it makes sense. So I'll focus on transverse waves here. So we'll say that this is my x-axis here, that's my y-axis there. So I'll focus on transverse waves. We'll write it down, and then we'll take a look at what that would mean. And it'll turn out that with longitudinal waves, they obey the exact same relationships anyway. So for my transverse wave, I'll go ahead and write it down, that the transverse displacement y as a position of x, the horizontal coordinate, and the time will be equal to the amplitude, which now we'll write as a capital Y since the waving is happening in the y direction, times the cosine of 2 pi times x over lambda minus or plus t over t. Now this bit here, 2 pi t over t, that's a simple harmonic oscillator, but we're going to have to look at this piece right here. So if I draw a wave, like so, y, and this is x, not t now, we'll say this is a snapshot graph at t equals 0. It's going to look something like this. And the distance from crest to crest is what we call the wavelength. And this letter is a lowercase Greek lambda, which you would draw like that. All right, so let's follow how this wave would propagate. So now let's say, and then t here is going to be the period of oscillation of a individual point. We'll see how that works out. So let's say that it's a quarter of a period later. Well, what's that going to do? If our wave is propagating to the right, it'll turn out that we need the minus sign. And to the left, we'll need the plus sign here. And honestly, I just remember that by thinking that's opposite of what you think it should be. Well, in that case, I have subtracted, let's see if this is t over 4. This becomes minus a quarter times 2 pi. I've subtracted 2 pi, so my cosine has now become a sine. So here would be a crest, here would be an inflection point, we'd have a trough there, we'd have a crest there, and so forth. All right. And let's try this for half a period. All right, so for half a period, putting capital T over 2 here, this will give me a half. We're going to the right, so minus a half times 2 pi will be minus pi. Well, cosine of something minus pi is the negative of the cosine. So that's going to look like that. And then we can repeat the exercise for 3t over 4. So for 3t over 4, it would end up looking like the negative of the sine. Oops, at that exact moment. Then finally, when we get back to t equals 1 period, well, after 1 period has elapsed, I've got big T over t here, that's 1 times 2 pi. The cosine of something minus 2 pi is just, well, cosine again, so guess what I'm going to do? Oops. Not bad. Hit cut when I meant to hit copy. And paste. There we go. It looks exactly the same. So how do we say that this is propagating to the right? Well, that's what happens if you start focusing on a crest. So let's look at this crest right here. And just to help make it clear, I will keep drawing X's on it as it ends up moving to the right. Oops. There we go. And so we see that in 1 period of oscillation, in 1 period of oscillation, the wave moved to the right 1 wavelength. And so just to clarify what I mean by oscillation here, let's focus on a specific point on the wave. So here, let's use, yeah, that color will do. That won't be better. All right. I'm going to draw boxes just around the exact point. And then what we're going to do is we're going to make what's called a history graph. So these are called snapshot graphs, which show you the whole wave at one specific point in time. We'll then make a history graph of x equals 0 for all time. So over here, we'll just say, all right, this is x equals 0, and now I'm plotting y versus t for all time. And what we got is we started out at big Y, then 0, then negative Y, then 0, then finally back up to big Y. Hey, what do you know? That looks like a simple harmonic oscillator. And that is indeed the case. Every point on a wave is executing simple harmonic motion about its equilibrium position. So, but now we can meaningfully define the speed of the wave. Say, look, the crest traveled one wavelength over one period of oscillation. So we can write that the speed of the wave is equal to the wavelength over the period of oscillation. We had already defined that the frequency was 1 over the period. So the usual way we do this is we substitute for 1 over t just f, and we write v equals the frequency times the wavelength. So to find the speed of any wave, you take the frequency and you multiply it by the wavelength. Or if you have the speed of the wave, either experimentally or derived theoretically, you can relate the frequency of a wave to its wavelength. So to just give a quick example of that, the speed of sound is 343 meters per second. So, well, actually, yeah. Speed of sound is about 343 meters per second at NTP. So if, say, I had I was emitting a tone of frequency 646 hertz, what would be the wavelength? Well, we can say v equals f lambda. Solve for lambda is v over f here. So it'd be 343 meters per second over 646 hertz. Now hertz is dimensionally 1 over seconds, so that will leave us with just meters. And we get that it's half a meter long. So by reference, concert A is 440 hertz. So that's roughly in the middle of musical notes. So pretty much most of the music you listen to has wavelengths on the order of centimeters up to maybe about a meter, or up to, maybe 10 meters or so at most. Okay, now there are some relations for these, like for instance, continuing off of our speed of sound. You can derive, and it's a very tedious derivation, that the speed of sound depends on the temperature and on the mass of the particle. And this gamma is a number that reflects the kind of bond structure that the molecule has in question. For air, this works out to be about 331 meters per second times the square root of the temperature over 273 Kelvin. So in air at NTP, 20 degrees C, that's 343 meters per second. At STP, 0 degrees C or 273 Kelvin, it's 331 meters per second. Now, you'll notice that this goes as this inverse is the square root of the mass. This is a recurring theme. If you were to solve for the speed of a wave on a string, and if you've seen any such derivation, it's probably had a fair amount of fibbing to it. solving for the speed of a wave on a string is something that you tend to do at the end of an upper level undergraduate classical mechanics course. I'll write T sub S here to deconfuse it from temperature. This is the tension in the string. And over mu, which is the linear mass density. So this is the mass of the string over its length. And that it so the material property shows up in how dense the string is, and then the greater the tension, the higher the wave speed. So for instance, when you tune a guitar, let's say you want the note to get higher. You would increase the tension. The wavelength, as we'll see in a future video, is directly proportional to the length of the guitar, but there's more to it that we'll have to get to. So it'd say, okay, the frequency is V over the wavelength. So as you increase the tension in the string, you increase the speed of the wave in the string, and that makes the frequency go up. So that's how you tune a guitar. So one last bit here to think about is, let's say you have a wave that's traveling along, and to make the example concrete, let's say it's going down a fairly thick string, and then we join it to a fairly thin string, okay? So like that. So what would happen, what's going to happen to the wave, to our wave here? Will the frequency, will the wavelength change? The frequency change? Both of them, or neither? Okay, it turns out that only the wavelength will change. The deal here is that, yes, because we went from a fat string to a thin string, we decreased the linear mass density of the string, so that changed the speed of the wave. But this is different than the guitar example. So the thing to remember is that if the speed of a wave changes, only the frequency changes, not the wavelength. And the story that I was taught to remember that was to think about a very well organized jailbreak. So here is the tower. Yeah, here is the prison wall. And let's say the prisoners discover a flaw in the security system that allows them to sneak out past the wall once every minute. So every minute a prisoner makes it through the defect in the wall design and is on the other side. Now, let's say they're on a road. If they're on a road, they can run a pretty good distance in a minute. So this is 1 minute later, here's where our prisoner would be. And then another minute later, there's where our prisoner would be. Now they don't want to run down the road forever because obviously the guards will come after them. So they first run into a farmer's field. Well, you can't run down a farmer's field as fast as you could run down a road. So in 1 minute, our prisoners are covering less ground. And then at the other end of the farmer's field, it turns out the ground goes swampy. You can't cover even as much ground as that then. And so every minute, the prisoners are barely making any headway. So then over here, the guards are capturing the prisoners. That's supposed to be a paddy wagon. Yeah, that didn't work out too good. Anyway, the guards are capturing the prisoners. At what rate are they going to capture them? 1 a minute. You make them at 1 a minute, you catch them at 1 a minute. So the frequency stays so if the speed of a wave changes, the frequency stays the same, but you can see that the wavelength will change. Okay, so in the next video we'll introduce the principle of superposition and start to look at how waves can interfere. Catch you in the next one.